Welcome to today's session. In this problem walkthrough, we will explore a fascinating coding challenge called Hexspeak. The goal of this problem is to convert a given decimal number into its hexadecimal representation and check if it can be interpreted as a valid Hexspeak string. Let's dive in and solve this step by step. Hexadecimal numbers are represented in base 16, meaning they use the digits 0 through 9, and the letters A through F to represent values from 10 to 15. In this problem, we need to convert a given decimal number into its hexadecimal equivalent and determine if the result meets the criteria for a valid Hexspeak string. A Hexspeak string is considered valid only if it contains specific characters, A, B, C, D, E, F, I, and O. Here, I corresponds to the digit 1, and O corresponds to the digit 0. Any other digit in the hexadecimal representation would make the string invalid. The goal is to return the converted Hexspeak string if it is valid, or error if it is not. The input to the problem is a positive decimal number provided as a string, and the output is either the valid Hexspeak string or the string error. The output format is straightforward. It will be a single string, either the valid Hexspeak string based on the conversion process or the string error if the given number does not meet the criteria. Let's look at some examples to understand this better. In the first example, the input is number equals 257. First, we convert 257 from decimal to hexadecimal, which results in 101 in base 16. Then, we replace the digit 1 with I and the digit 0 with O, giving us the string IOI. Since IOI contains only valid Hexspeak characters, the output is IOI. In the second example, the input is number equals 3. Converting 3 from decimal to hexadecimal results in 3 in base 16. However, the digit 3 is not one of the allowed Hexspeak characters. As a result, the output for this example is error. This demonstrates that any digit outside the valid Hexspeak characters automatically invalidates the string, regardless of its length or simplicity. Now, consider the third example where the input is a much larger number equals 1000000000000. Converting this number from decimal to hexadecimal results in the string E8D4A51000. While the letters E and A are valid Hexspeak characters, the digits 8, 4, and 5 are not. Since the presence of any invalid digit disqualifies the entire string, the output in this case is error. This example highlights the importance of checking every character in the hexadecimal representation to ensure it adheres to the Hexspeak rules. Finally, let's consider some edge cases that you might encounter. If the input is at the lower boundary, such as number equals 1, the conversion results in 1, which is valid as it maps to I in Hexspeak. Another edge case involves very large inputs, like number equals 10^12. Here, you need to ensure that the program efficiently handles large conversions without issues like overflow. Additionally, cases where the hexadecimal conversion contains invalid digits, such as number equals 272 resulting in 110, must be handled correctly by returning error. On the other hand, smaller numbers that map directly to valid Hexspeak, like number equals 15 converting to F, should be returned as is. These scenarios emphasize the importance of validating each character after conversion while handling a wide range of inputs effectively. To solve the Hexspeak problem, our goal is to take a positive decimal number, provided as a string, and convert it into its hexadecimal representation. Once converted, we need to determine if the resulting string qualifies as valid Hexspeak. A Hexspeak string is valid only if it uses specific characters, A, B, C, D, E, F, I, and O. Here, I and O are derived from the digits 1 and 0, respectively. If the hexadecimal representation contains any digits other than 0 or 1, such as 2 through 9, the number is considered invalid for Hexspeak. This problem challenges us to ensure that the conversion and validation steps are both efficient and accurate. One approach to solving this problem is to use brute force conversion and validation. The idea here is to rely on built-in functions to convert the decimal number into its hexadecimal representation and then validate the resulting string. First, we convert the decimal number into a hexadecimal string using a function like hex in Python. Next, we ensure all letters in the hexadecimal string are uppercase, which aligns with the Hexspeak format. Then, we replace any 0 with O and 1 with I, as specified in the problem. Finally, we validate the transformed string to check if it contains only the allowed characters, A through F, I, and O. If it doesn't, we return error, otherwise, we return the valid Hexspeak string. This approach is straightforward and efficient, with a time complexity of O log n, since the length of the hexadecimal string corresponds to the logarithm of the decimal number. While simple, this method benefits from leveraging built-in functions, making it less error-prone and easier to implement. Another method to tackle the problem is by manually performing the base conversion from decimal to hexadecimal. Instead of relying on built-in functions, we calculate the hexadecimal representation ourselves through repeated division. Starting with the decimal number, we repeatedly divide it by 16, keeping track of the remainders. These remainders correspond to the hexadecimal digits, which we map to their respective characters. Numbers 0 through 9 remain as is, while numbers 10 through 15 are mapped to the letters A through F. Once we've collected all the remainders, we reverse their order to get the proper hexadecimal string. After this, we replace 0 with O and 1 with I, and validate the string against the Hexspeak criteria. Like the brute force method, this approach has a time complexity of O log n. However, it's more verbose and prone to errors, as it requires manually handling each step of the conversion. While this method offers greater control, modern programming tools make it less practical compared to built-in solutions. A third approach introduces an optimization by integrating validation directly into the conversion process. Using this method, we can immediately reject invalid inputs during the conversion. First, we convert the decimal number to its hexadecimal representation using a built-in function. Then, instead of processing the entire string at once, we iterate through it character by character. As we encounter each digit, we check if it is valid. Characters must be 0, 1, or within A to F. If any invalid character is found, we terminate the process early and return error. For valid digits, we replace 0 with O and 1 with I directly during this iteration. If no invalid characters are found, we construct the final Hexspeak string and return it. This approach also has a time complexity of O log en, but can save unnecessary processing by stopping as soon as invalid input is detected. However, this in-place validation makes the code slightly less readable compared to the brute force method, which processes each step sequentially. Ultimately, we selected the brute force conversion and validation approach as the best strategy for this problem. Its simplicity and reliance on built-in functions make it easy to implement and less prone to errors, which is especially beneficial for quick development. While the optimized validation approach offers early termination, the performance gains are negligible for reasonably sized inputs, making readability a stronger priority. The manual base conversion approach, though educational, is unnecessarily verbose and error-prone when compared to modern tools. One key insight for this problem is recognizing that only the digits 0 and 1 require special handling, simplifying the validation logic significantly. Among the three approaches, the brute force method strikes the ideal balance between clarity, correctness, and efficiency, making it the most practical choice for solving the Hexspeak problem. The Hexspeak problem challenges us to convert a given positive decimal number into its hexadecimal representation and then determine if the result qualifies as a valid Hexspeak string. For a string to be valid, it must only use the characters A through F, along with the digits 1 and 0, where 1 is interpreted as I and 0 is interpreted as O. If any other characters, such as 2, 3, or other digits beyond 1 and 0, appear in the hexadecimal output, the string is considered invalid. To solve this, we start by parsing the input to ensure it is a positive decimal integer. Then, we use Python's built-in hex function to convert the decimal number to its hexadecimal equivalent. This function makes the process straightforward and handles large integers seamlessly. Afterward, we strip the 0x prefix that Python includes in the output of hex, and convert the resulting string to uppercase, as Hexspeak uses uppercase letters exclusively. This prepares us for the validation and transformation steps ahead. Once we have the hexadecimal string, the next step is to validate its characters. To do this, we iterate through each character in the string and check if it belongs to the set of allowed Hexspeak characters, which includes A, B, C, D, E, F, 1, and 0. This approach ensures that any disallowed character, such as 2 or 3, will immediately mark the string as invalid. If all characters pass validation, we proceed to the transformation step, where we replace the digits 1 and 0 with their Hexspeak equivalents, I and O, respectively. This replacement creates the final Hexspeak string. At the end of this process, we return the transformed string if it is valid. Otherwise, if any invalid characters were found during validation, we return the string error to indicate the input cannot be represented as Hexspeak. Now, let's discuss some key insights about this problem. First, hexadecimal representation uses the numbers 0 through 9 and the letters A through F. In Hexspeak, the digits 1 and 0 are reinterpreted as I and O, respectively, making the output more human-readable. The validation step, where we check each character against the allowed set, is efficient, as it has a time complexity of O(n), where n is the length of the hexadecimal string. Similarly, the transformation step, where we replace 1 with I and 0 with O, is also linear in time. Several edge cases are worth noting. For example, if the input is 0, the hexadecimal output is also 0, which directly translates to O. If the input is 1, it translates to I. Python's ability to handle large integers natively means we don't need special consideration for large inputs. Finally, any decimal numbers that result in disallowed hexadecimal characters, like 2 through 9, will be flagged as invalid immediately. We also make use of efficient data structures like sets for validation, as they allow constant time membership checks, and strings for transformation, which are simple to manipulate. Let's walk through a couple of examples to solidify our understanding. First, consider the input 257. When we convert it to hexadecimal, it becomes 101. Next, we validate each character. 1, 0, and 1 are all in the allowed set, so the string is valid. We then replace 1 with I and 0 with O, resulting in the Hexspeak string IOI. This is our final output. Now, take the input 3. Converting it to hexadecimal gives 3, but 3 is not in the allowed set of Hexspeak characters. As a result, the string is deemed invalid, and we return error for this input. These examples highlight the straightforward nature of the algorithm while emphasizing the importance of validation in determining whether a string qualifies as Hexspeak. To conclude, let's analyze the complexity of the solution. The time complexity is O(n), where n is the length of the hexadecimal string. This accounts for the conversion, validation, and transformation steps, all of which operate linearly with respect to the string length. The space complexity is also O(n), since we create a new string to store the Hexspeak result. There are several optimizations to keep in mind. For instance, we can terminate the validation process as soon as an invalid character is detected, avoiding unnecessary computations. Additionally, validation and replacement can be combined into a single iteration to further reduce redundant passes over the string. Lastly, leveraging Python's built-in functions, such as hex, for conversion and string methods for transformation, ensures the solution is both efficient and concise. These optimizations make the algorithm robust and well-suited for handling a wide range of inputs, including edge cases and large numbers. This solution implements the problem Hexspeak by converting a given decimal number into its hexadecimal representation and validating it against the Hexspeak criteria. The solution starts by converting the input, which is a string, into an integer. This ensures the number is in a usable numeric form for conversion. Next, it converts the integer into its hexadecimal string representation using Python's built-in hex function, slicing off the 0x prefix and converting the result to uppercase to match the Hexspeak format. The solution then defines a mapping dictionary that explicitly maps valid Hexspeak characters, AF, 1, 0, to their corresponding Hexspeak interpretations, AF, I, O. It iterates through each character of the hexadecimal string, checking if it exists in the mapping. If the character is valid, it appends the mapped value to the resulting string. If an invalid character, e.g., 2, 3, is encountered, the function immediately returns error, as the string cannot be a valid Hexspeak representation. The solution ensures clarity, handles edge cases like invalid characters, and directly returns the converted Hexspeak string if all characters are valid. The algorithm efficiently processes the input in O(n) time, where n is the length of the hexadecimal representation, making it suitable for large inputs. Here, we begin by defining the method toHexspeak, which takes a string input number representing a decimal number. First, we parse the string into a long integer using long_parseLong. This allows us to handle large numbers without losing precision. Next, we convert this number into its hexadecimal representation using long_toHex string, which returns a lowercase hexadecimal string. To make it suitable for Hexspeak, we convert it to uppercase using the toUpperCase method. After this, we create a mapping to define which characters are valid in Hexspeak. For example, the digits 1 and 0 are mapped to the letters I and O, respectively, while the characters A through F remain unchanged. This mapping ensures that we can transform the hexadecimal string into a valid Hexspeak format. Finally, we initialize a string builder to construct the Hexspeak string. Using a for loop, we iterate over each character in the hexadecimal string and check if it's in our mapping. If it is, we append the corresponding Hexspeak character to the string builder. If during the iteration we encounter a character that is not part of our predefined Hexspeak mapping, we immediately return an error string, error. This ensures that any invalid input that cannot be represented in Hexspeak is rejected. On the other hand, if all characters in the hexadecimal string are valid, we complete the iteration and convert the string builder to a string using the toString method. This string, which represents the Hexspeak version of the input number, is then returned as the final result. By carefully handling invalid cases and leveraging the mapping, this implementation guarantees that the output adheres strictly to the rules of Hexspeak. In this example, we start with the input string number equal to 257. The first step is to convert this string into an integer using Python's int function. This gives us the value 257 as a decimal number. Next, we convert this decimal number to its hexadecimal representation using the hex function. The result, after removing the 0x prefix and converting to uppercase, is the string 101. Now, we begin the process of mapping each hexadecimal character to its corresponding Hexspeak equivalent. We initialize an empty string called Hexspeak_str to build the Hexspeak result. For the first character, 1, we refer to the mapping and find that it corresponds to I. This means we append I to our Hexspeak_str, leaving us with I at this point. Continuing with the Hexspeak mapping, we look at the second character in the hexadecimal string, which is 0. According to the mapping, 0 corresponds to O, so we append O to Hexspeak_str. Now, the string becomes IO. Finally, we process the third character, 1, which again maps to I. Appending this to our result gives us the final Hexspeak string IOI. Since all characters in the input were valid and successfully mapped, we return IOI as the output. For the next example, we examine the input number equal to 3. The first step here is to convert this string into an integer, which results in the decimal value 3. This sets the stage for the next steps of the conversion process. With the decimal value 3 in hand, we convert it to its hexadecimal representation using Python's hex function. After removing the 0x prefix and converting the result to uppercase, the hexadecimal string becomes 3. Now, we need to map this single character to its Hexspeak equivalent. However, when we check the mapping, we find that 3 does not correspond to any valid Hexspeak character. As a result, we immediately return error because the input cannot be translated into a valid Hexspeak string. This demonstrates how the solution handles cases where the input contains characters that do not meet the Hexspeak criteria. In the next example, we analyze the input number equal to 48,879. First, we convert the string 48,879 into an integer using int, resulting in the decimal value 48879. Next, we convert this decimal number into its hexadecimal representation using the hex function. Removing the 0x prefix and converting to uppercase gives us the string beef. Now, we begin constructing the Hexspeak representation. We initialize an empty string called Hexspeak_str and start processing the characters in beef. The first character is B, which is valid in Hexspeak and maps directly to B. We append this to Hexspeak_str, so the string now contains B. Continuing with the Hexspeak conversion for beef, we move to the second character, E. According to the mapping, E is a valid character and maps directly to E, so we append it to Hexspeak_str. This updates the string to B. The next character is another E, which again maps to E. Appending this results in BEE. Finally, we process the last character, F, which is valid and maps directly to F. Adding this to Hexspeak_str gives us the final Hexspeak string beef. Since all the characters in the input were valid and successfully mapped, we return beef as the output of this example. To summarize, this solution works by first converting the input string number into a decimal integer. It then converts the decimal value into its hexadecimal representation and processes each character to construct the Hexspeak string using a predefined mapping. If, at any point, a character is encountered that does not correspond to a valid Hexspeak character, the solution immediately returns error. This approach ensures that the output strictly adheres to the Hexspeak rules, providing either a valid Hexspeak string or an error message when the input cannot be represented as Hexspeak. To analyze the time complexity of the Hexspeak problem, we can break it into distinct steps. First, converting the input string number to a decimal integer using the int number function involves parsing its digits. This operation depends on the length of the string, which is proportional to the number of digits, denoted as d. Since the number of digits in a number grows logarithmically with its value, this step has a time complexity of approximately O log 10 n, where n represents the numerical value of the input. Next, the conversion of this decimal integer to its hexadecimal form using the hex decimal_number function has a time complexity of O log 16 n, as the number of hexadecimal digits also grows logarithmically with n. Additional operations like string slicing and converting the result to uppercase are linear in relation to the hexadecimal string's length, which is O log 16 n. Therefore, this entire step remains O log 16 n. The next significant operation is mapping the hexadecimal characters to their corresponding Hexspeak values. Here, we iterate through each character of the hexadecimal string, perform a dictionary lookup for the Hexspeak mapping, and append the result to the output string. Since the hexadecimal string length is O log 16 n, and each dictionary lookup is O1, the overall time complexity of this step is O log 16 n. Finally, returning the Hexspeak string or error is a simple operation with O1 complexity. When combining all these steps, the most time-consuming operations are the number conversion and character mapping, both of which scale with O log 16 n. Since logarithms with different bases differ only by a constant factor, we can simplify the time complexity to O log n. Analyzing the space complexity, the input string number requires storage proportional to its length, which is O d, where d is the number of digits in the input. As previously mentioned, d is proportional to log 10 n. Then, the decimal_number variable holds the integer representation of the input. In Python, integers are dynamically sized, but the space required for a single integer is negligible and considered O1. The hexadecimal representation of the number is stored as a string, with a length proportional to O log 16 n. Similarly, the final Hexspeak string, which is derived from mapping the hexadecimal characters, also has a length of O log 16 n. Additionally, the Hexspeak mapping dictionary is constant-sized with only 8 key-value pairs, requiring O1 space. Combining these, the dominant space usage arises from the input string, hexadecimal string, and Hexspeak string, all of which scale as O log n. When comparing approaches, a naive solution for Hexspeak might involve manually converting the number to hexadecimal, validating each digit, and constructing the output string. While this would still result in a time complexity of O log n, it would likely involve more intermediate steps and additional overhead. The optimized approach we've discussed leverages Python's built-in functions for conversions and string manipulations, which are highly efficient and reduce redundancy. When analyzing the best, average, and worst cases, the best case occurs with minimal input, such as 1, where operations require constant time due to the small size. In the average case, the input grows logarithmically with the value of number, leading to O log n complexity. The worst case also scales logarithmically, as the operations depend on the length of the input and the resulting hexadecimal representation. Thus, all cases are bounded by O log n time complexity. In summary, the provided solution is both efficient and optimal for the Hexspeak problem. With a time complexity of O log n and a space complexity of O log n, the solution scales logarithmically with the size of the input number. This ensures that the algorithm remains performant even for large inputs. By leveraging Python's built-in functions for number conversion and string manipulation, the implementation minimizes overhead and avoids unnecessary computations, resulting in a clean and effective solution. These optimal complexities align well with the requirements of the problem, making the approach robust and highly suitable for real-world scenarios. When solving Hexspeak problems, it's important to avoid some common pitfalls. First, be mindful of the constraints of the hexadecimal system. In Hexspeak, only the letters A through F and specific digit mappings like 0 to O and 1 to I are valid. Any other digit, such as 2 through 9, makes the string invalid, so ensure you validate every character after conversion. Another common mistake is not handling leading zeros properly. For example, when converting a number like 0001, the leading zeros should be dropped in the final output, as hexadecimal numbers don't preserve them. Additionally, working with large numbers near the 64-bit limit can lead to overflow errors if you rely on direct integer arithmetic. To avoid this, consider working with strings instead. It's also crucial to validate the input number string to ensure it's non-negative, numeric, and within constraints. Finally, inefficient implementations, such as repeatedly searching for valid Hexspeak characters rather than using optimized data structures like hash sets, can unnecessarily increase runtime. Prioritizing efficiency and correctness will help you avoid these issues. Hexadecimal conversion problems like Hexspeak are often used in interviews to test your understanding of number systems and string manipulations. A key insight is to become comfortable with manual base conversions and character mappings, since these are fundamental to solving such problems. Recognizing patterns is also essential. For instance, in Hexspeak, the mapping of 0 to O and 1 to I is a critical pattern that must be implemented correctly to ensure validity. Edge cases are another important consideration. You might encounter minimal inputs like 1, very large numbers, or invalid inputs containing non-digit characters, so make sure your solution accounts for these scenarios. Lastly, focus on optimization. If the input size or range is significant, such as numbers up to 10 to the power of 12, your solution needs to handle constraints efficiently. Avoid unnecessary operations and redundant validations to ensure your code runs smoothly under all conditions. Understanding Hexspeak can also help you tackle related problems that involve similar concepts of base conversion and character mapping. For example, LeetCode 168, the Excel sheet column title problem, requires converting numbers into a custom base representation, which relies on similar principles. Then there's LeetCode 171, the reverse of this process, where you convert from a custom base back to decimal. Another related problem is LeetCode 12, integer to Roman, which involves mapping integers to a specific non-standard representation system, much like Hexspeak. Finally, LeetCode 273, integer to English words, challenges you to convert numbers into a completely different format, requiring careful character mapping and handling of edge cases. These problems share underlying themes with Hexspeak, so mastering one can provide insights into solving the others. There are multiple approaches to solving Hexspeak problems, each with its own trade-offs. A straightforward method is the brute force approach, where you convert the number to hexadecimal and then manually validate each character to ensure it meets Hexspeak constraints. While this is simple to implement, it may involve redundant checks, making it less efficient for large inputs. A better alternative is the pre-mapped conversion approach. Here, you use a dictionary to pre-map valid Hexspeak characters such as 0 to O, 1 to I, and A to F, and reject any invalid characters like 2 through 9. This method simplifies validation and is faster to execute, though it requires some initial setup. For advanced users, bitwise operations can be used to extract hexadecimal digits directly. This minimizes computation and is highly efficient, but it may reduce code readability and be prone to errors for those less experienced. Choosing the right approach depends on your familiarity with these techniques and the specific constraints of the problem. Great work! Today, we solved the Hexspeak problem by converting a decimal number to its hexadecimal form and validating it as Hexspeak. We reviewed base conversions, string processing, and validation techniques. Thank you for joining, and see you in the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!